Okay, then probably you noticed that yesterday evening I put on Blackboard the solutions of the first homework. Did you notice that? No. Because on Sunday you are not supposed to work, right? You are all very, how is that called? Very Reformed Christians. Do you know that part of the Dutch culture? The Bible Belt? Yeah. Okay. Then I don't see any student, but I have to do my duty, right?
There are 2 students in all.
Okay, then if there are no students,
No, there are 2.
okay, there are.
Not in the picture.
Okay, that's great. That's good. Okay, we were just starting the discussion. Okay, I can see the parking place. Okay, it's brilliant. Okay, welcome guys. That's a different way to celebrate a carnival, right?
Next week.
Next week, okay. But why do you get vacation this week?
But please start your presentation.
Okay. Am I not allowed to ask questions?
Oh yeah, of course, but you don't have a PowerPoint presentation or something?
Yes, I do. It's on screen.
Not on ours.
Oh.
Probably you have
You have to
to
push the green button of the remote control.
I don't think so, but I can try it. Turn. No, that's turn off. It should be okay. Laptop 1, video conference.
Yeah, there it is.
I didn't do much, but I just pushed a button on the menu. But it's brilliant. Okay. Then let's forget the carnival and let us concentrate on the homework. Then I put the solutions on Blackboard, but I would like to discuss a bit the solutions with you. And I will start by looking at the questions. Then just a word of advice. Whenever you are reading a question, do not jump directly to the solution, assuming that you understood the question and there is a direct link between one concept and another concept. Good morning. Sometimes, you know, there are false friends. Like if you speak German and you hear they or mir, it's the other way than in Dutch, you know. Sea and lake. They are the other way around. And this is called a false friend in languages. There are many of those. Now, if you look at the first question, it's about making a conversion. And then you have to convert a number from a radix minus 2 into radix hexadecimal, then is radix 16. My first reaction will be to start doing calculations, right? Divisions, multiplications, whatever, mostly divisions, because I know that when I do conversion from a radix to another, I have to do some kind of division or multiplication. If I go into that, I will eventually get to the solution. But it won't really be the right one because I have to make some observation. There is a nice relation between the two radixes. I deal with radix minus 2 and radix 16. The only thing which is bothering me is the minus 2. If I know that radix would be 2, it's very simple. We had even discussed that in the class. If I have a number in radix 2 and I want to make it in radix 16, it's trivial because instead of taking 1 bit at a time, I take 4 bits at a time, and they will give me a digit in radix 16. Then my first problem will be to get rid of the minus 2, then to convert from minus 2 in radix 2. How do I do that? If I am in radix 2, all the bits will have 2 at power something as weight. In minus 2, they will have minus 2 at power something weight, which means that the odd and even positions will have negative or positive weight. Then if I want to convert from radix minus 2, hello, what are you doing? Then if I want to convert from minus 2 into 2, the straightforward solution will be to replace the bits in the odd position with minus whatever they are. Because in that way I will absorb the sign into the digit, and then I am in radix 2. Then this is okay, this is okay because it's a 0, this is okay, this is a negative 1. And instead of leaving it a 1, I will write a minus 1. I will conserve the value because this is what I want, to conserve the value. If I lose the value, I'm not doing a good job. Then if I do this kind of calculations, I get into, okay, now, into this. You see, what I did is I took all the positions where I had a negative weight, and I replaced the 0 with 0 because it doesn't matter, and the 1 with minus 1. And now I have a nice representation of my number in radix 2. Then my first step was very simple. If I would have done divisions and stuff like that, I would have made a lot of mistakes in calculations for sure. And it would have taken me a lot of time. Now my next step will be to do the standard trick. Then I am in radix 2, I want to go in radix 16, which means that I will group those guys in groups of 4 bits, which will result in this kind of representation. Now I have to compute for each and every hexadecimal digit the value, the right value. And I will keep into calculation the sign of the bits. All of them are weighted with a positive, but some of them carry the negative information into their sign. They are 1 or minus 1. Then let's say this one is actually minus 8 plus 4. This is 0 plus 1. Then it's minus 8 plus 5 is minus 3. This is minus 2. This is again minus 8 plus 4 minus 2 plus 1. This is minus 5. And this is 0. Which means, again with very simple calculation, I arrive to a radix 16 representation. However, this is not really hexadecimal. In hexadecimal, I have digits from 0 to F. Right? And what I have to do is I have to get rid of those illegitimate digits. And how do? I use, you know, my standard trick. I write minus 3 as a borrow from the next position, and whatever will be the result of that. Then I'm borrowing 16 from here, then and in here I will have 16 minus 3, which will give me 13. This will be still okay because it's minus 16 plus 13, which is giving me minus 3. And then I managed to make the first conversion. I will do the same for this. I will apply the same trick for this. And eventually my number will be ADD. Is it clear? Okay? Then what I did was no calculations whatsoever. Then again, my advice is whenever you have to address a problem in exam, but also in other situations later on, for me it's more important later on. For you it's more important in the exam, as far as I cannot assume. Just think twice before you start the solution. If I would have tried to do it according to the method in the book, straightforward, without observing the relation between the two radixes, that they are both power of 2, I would have had for sure a lot of troubles in doing the calculation first, and then the chance to get to this solution would have been a lot smaller. Not that it will not give you the same solution. If you manage to carry on an error-free derivation, you'll get to the same solution. Now, I have a funny question. Should I ask it or not? Did you solve this question? In which way? I'm just curious, you know. Yes?
The stupid way.
The stupid way. And did you get to this? I didn't say it was stupid. No. It's not stupid. It is what is called brute force approach. If you have a lot of muscles, you know, you can do it. You know, there is a joke that you can classify engineers in smart and strong engineers. Okay? I want you to be smart engineers. There's not a problem that you took that approach. It will be a problem if the next question, which is similar to that, will be solved in the same approach. But I really appreciate the fact that you say it in public, that you did it, which is good. Your colleagues also?
The same question is also possible.
Okay. This is, you know, the easy road. If you arrive to the right solution, doesn't matter the road. But, you know, it's good to save energy. Now, is it clear, the discussion? Eindhoven, are you with us? Okay, great. Questions? No, brilliant. It took me a lot of time to solve it, actually to type it. Okay. It was a follow-up discussion, and I think there's, what was the next question? Okay. Now you have to repeat for minus 16. Then in order to do it for minus 16, you have to make the same observation, that essentially, if you deal with minus 16, this is positive, this is negative, this is positive. And you have to do something in order to write it in such a way that you get a negative information in this position. And how do you do that? It's simple. You make a carry to the next position, and you get here a negative digit. Then you transform this into b minus 3d, which is now in radix 16. But when you move into radix minus 16, those will conserve, and this will just move the sign into the weight of the position. And then you are done. Then essentially there are two tricks here in the question. I mean, the choice for the question was not random. Then one, it's about grouping bits when you transfer from one radix to the other. And the other one, it's playing with sign between the position sign and the digit sign. If you got those two messages, then I'll be happy. Okay? Yeah, you don't see that, but I have some troubles with my screen. Hopefully it will stay with us until the end of the class at least. Okay, this is a typical logic design question. You have two numbers and you have to compare them. And most of the time what you have is a box which is taking the numbers x and y, and you have here 2 or 3 signals, great, low, equal. Actually you can derive equal from those two. If this is not true, this is not true, then you have equal. it will be slightly longer the time because you have to wait for those to be computed. Now, the way you make the comparison very much depends on the way the numbers are represented. If you deal with sign numbers, biased numbers, or any kind of numbers, you have to think about the way they are represented. In here, we have the easiest solution because we deal with sign numbers. And when I compare sign numbers, unsigned numbers, sorry, then there is no sign. Then, if I want to compare the numbers, I always start from the most significant bit. While when I'm doing an addition, I'm always starting from least significant bit because carries are propagating towards the most significant bit. When I do a comparison, I always start from here. Then I compare the first positions. If they are equal, I have to go to the next position. If one of them is larger, and I'm only interested in, in that fact, I can stop. If they are equal, I have to go to the next position. And in here again, they were equal, and now if this one is larger, I know the solution. And I can do that until the end of the number. And the first position, which will signal me that x is larger than y, will determine the comparison. Now, this will work for that kind of things. If you want to compare two RMS numbers, you remember this will not function. Now, how do you implement that? There are many ways to do it. You can write Boolean equations and do different kind of things. And what I have, it's that way. Okay? Then it is quite advisable to simplify the calculation by means of doing some kind of additional evaluations. Then your goal is to evaluate whether or not x is larger than y or x is smaller than y. This is my target. But before hitting the target, I also can do some lateral thinking, which will say, how can I hit my target in a simple way by spending some effort in computing things which are useful? This is making a kind of strange noise. Then, and in this case, it is useful to first compute some signals, some auxiliary signals, which are saying whether or not the numbers are equal, starting from the most significant position to the position which I'm evaluating. Then if I am, then x will be greater, it's on the most significant bit, x is larger, which because I am in binary, it's reflected by that. X3 will be 1, and this will be 0. This will be 1 and will dominate the rest. If this is not 1, I will move to the next position. And I apply the same technique then if this is 1 and this is 0, but I need an extra condition. And the extra condition will be that on positions which are on a more significant position than my current position, the numbers are equal. And I am computing that with this auxiliary signal equal from 3 to 3. I have another auxiliary position from 3 to 2 and from 3 to 1. This is an implementation. The same story for y. I could also draw some K-maps and try to simplify directly. I see some smiling. At least you still remember what K-maps are. You know, Carnot maps. Not to make a confusion with the other Carnot. Do you know which is the other Carnot that I'm referring at? Do you drive a car? Have you ever been inside a car? There is an engine, right? You never studied thermodynamics? Carnot maps? Carnot diagrams? It's the same kind of, it's a different Carnot. It's about the relation between temperature, volume, and pressure, okay? Come on, guys. Don't depress me. I cannot believe that you never studied that kind of, neither in high school. It's about gases. It's the basic principle of the functioning of the engines. Okay. Hello, good morning. Welcome. Then it's a different Carnot. Yes. Okay. Can you hear me? I see you can hear me. You can see the slides. Everything is brilliant. Then I have to return to my story. Then we are discussing about the solution to homework 1. Then this is an implementation, but it's not the only one. You could get different kind of equations to get the same solution. Now, that was again a kind of thinking a bit beyond the question. And this is another example on how can I simplify my life, conceptually speaking. Okay, now, that one had also another part, and the part was about how to compare 16-bit numbers, if I'm not mistaken. No, that's not the one. Okay, then the second part was how to use 4-bit comparators to compare 16-bit numbers. Then I have this building block, which is functioning. I already implemented. It's like it's already in an FPGA. And I want now to apply a hierarchical construction to make a 16-bit comparator. There are again many possible solutions, but this is one of them. What I'm doing is I'm applying the same principle. I am looking at the 4 most significant bits of my numbers, and I make a comparison of those. And that will give me a result. If x is larger than y, I'll get here a 1, otherwise a 0. If smaller, 0 or a 1. Then this output of this comparator, it's actually telling me about the first 4 bits, and is compressing them into 1-bit position. I use the result of this guy in order to inspect the next 4 bits. Actually, if this is clear, I can also stop the calculation. If here I have 1, 0 or 0, 1, I already know which one is larger. But if in here I have a 0, 0, I don't know. Then I have to go further. And my design should work in all the situations. Then now what I'm doing is I'm taking the output of this guy, I'm taking 3 more positions, and I'm applying the same trick. And I am doing that until I arrive to the last group. Then what you see is that this is a kind of sequential approach. I'm not doing any kind of parallel processing, which it's somehow not that good. If I am designing asynchronous hardware, that's a good solution. Because whenever I'll get here at the output something which makes sense, I can stop. And I will continue the calculation only if required. If I'm designing asynchronous hardware, that's fine. If I'm designing synchronous hardware, I will always have to wait until the end of the calculation. Then it's not exactly a nice solution. And this is the answer to the last question, when now you have to compare, what do you have to compare? 28-bit numbers. And now the comparator is built as a tree. Remember from the prefix calculation last time, I was always happy with a tree. Then whenever I want a solution, I look for a tree. When I implement a gate with a large funine, I look for a tree. When I want to deal with the carry propagation in a nice way, I look for a tree. I'm doing the same here. And what I can do is say, okay, I have 28 bits. I divide 28 by 4, which will give me 7 comparators. And then I can take all of those and then construct the tree further. If I do that, this comparator, which will be now the second level, will not be fully utilized. Then, because I will have 3 inputs, 3 set of inputs, and this will be a 3-bit comparator. What I can do now is I can use this comparator to absorb some kind of calculation which I'm not really doing in the first position. This is an optimized design. The straightforward design would be 7 comparators in the top, 2 comparators in here, and then a final comparator which is taking 4 bits. Now my solution is a bit more tricky, and I'm saving a comparator without getting any penalty. This is engineering, okay? Because I always say that I don't care about the area, which is true. But sometimes I even care for a byte. You know, not a byte like when the fish is biting, a byte, you know, like 8 bits. Then if you would have done it with 7 here, it's no problem. This is just an optimization. Did you solve that problem?
Yeah, it was like 711.
It's okay. But will it be enough with 1, 1?
Yeah. In the second we can use
How come? Because in here,
You've compressed the lower part of the work in the second level, and the upper part is just wired through to the first stage.
okay, you can do that too. Actually, it's not the only solution, as I said again. The idea is to come with a solution which is fulfilling the requirements, which were not exactly clear. Then sometimes you have boundary conditions which are saying you have to do it within that kind of constraints. Okay? Then whenever you get a question in the exam, read it carefully. You know, it happened to me many times that I'm asking something and you answer a different thing. Like when I say, design a circuit which is doing that, write the logical equations, do not draw the circuit. What do you think I mostly see on the solutions? Just the circuit, no equations. Okay? Or I say, explain me the way you arrived to the result. What was your reasoning? And you give me the answer, 7, which is good, maybe. But if I don't see the way you arrived to the result, I cannot judge, you know, your solution. And speaking about that, when I check exams, I very much care for the way you approach the problem. Even if you get to a wrong solution, like number-wise, if your approach is okay, you still get points. Because this is engineering and it should be doing that. Okay, now next. Next was the story about converting from 2's complement. No, this is solution. Let's see what the question is, right? then I want to convert from 2's complement format into a biased representation. And the biased representation is 2 to the power k minus 1, backward and forward. This is essentially a very simple thing. Because if you look at the number, this one, the most significant bit, is carrying the information about a weight of 2 to the power k minus 1, if this one has k bits. Then if I want to transform from 2's complement into a biased representation, if I flip this bit, I have the bias. That's simple. And when I do it for 2 to the power k minus 1, I have to be careful because just flipping this bit is not enough. By flipping the bit, I am adding or subtracting too much. Then I have to make a compensation with the minus 1. This is the standard trick from 2's complement and 1's complement numbers. Okay? There is not that much I have to say. There is a thing, eventually, the fact that when I do this representation from 2's complement into a biased representation with a bias of 2 to the power k minus 1, some of the numbers which are representable in 2's complement, I cannot represent in the bias. Then I will have some exceptions. Book. Okay. Next question. Then, next question was about designing a carry-free addition. Okay, then I have a system, it's a radix set, and the digit set is from 0 to 15. Then essentially I'm doing radix 10 calculation, but the digit set is like in the hexadecimal calculation. I have a lot of freedom due to redundancy to do carry-free addition. And the first question was to find the relevant parameters for the addition in this system. On Blackboard, you have a slide about how to compute some constants. Did you see those? They were together in the same package, right? Then the hint was that you should use those. Also in the book, Parhami is using those constants, but he is kind of, hiding from you the way he's doing that. He's not doing any witchcraft. He's just using some formulas. Now, my first problem will be to determine the dynamic range for the transfer in such a way that I obtain a carry-free addition. That's the first step. The second step will be to design the adder. Because, I'm adding 2 digits. I get a positional sum, which now I have to rewrite as a transport, and the local sum, which I have now to add with the transport coming from the previous position. That's my job. Okay? Now, again, you can do it in different ways. You can also determine the range for the digits, for the transport and the rest by thinking. If I am adding numbers between 0 and 15, the result will be between 0 and 30. Then 30 is kind of too large, right? Then I have to generate transport of 0, 1, maybe, 2 also. Then I can determine the dynamic range from the transport just by thinking. If it is 30, I really have to make a transport of 2, which will be 20, but plus 10. 10 is a legitimate digit for the position, and a transport of 2 is the maximum transport that I should do. A transport of 3, it's also possible, but will it make sense? I mean, I can make a transport of 3, which will be, I write 30 as 3 plus 0. I can do that, but I'm making my life more complicated than it should. It's the only case when I can use 3. Now, if the transport is between 0 and 2, I have to do another restriction. If the transport can be 0, 2, after rewriting the sum, I have to be sure that the digit that I obtain is not larger than 13. Because 13 plus the worst case, which is 2, will give me 15. I'm on the boundary. If my digit after rewriting is larger than 13, I have a problem. It's not carry-free addition. Then by doing thinking, I arrive to determine the parameters for that addition. But I also can do some calculations for that, you know. Sometimes it's easier to apply a formula. Other times it's nicer and easier to do some thinking. Okay. Now, what I get is kind of this, right? Then the transfer range is 0, 2. I have to encode it in a certain way, because this encoding will have an influence on the way I'm doing the implementation. And my decision for the encoding is, because I have 0, 1, 2, I have to use 2 digits. And I can use them in different ways. If you use them different than I did, you will get a different solution, which will still be good. Now, I encode them 0, 1, 0, 1, 1. Then the sum of the 2 bits, it's actually giving me the value. Now, what I have to do is I have to determine the constants. I have 2 constants, then I have to split the dynamic range of my position sum in 3 regions. When I generate no transport, when I generate a transport for 1, and when I generate a transport for 2. Then this is the positional sum, which can be between 0 and 30. And I have to put some boundaries. Here there is a 0 transport, 1 transport, 2 transport. There is no unique solution for that position in here. Then I can put this, according to the calculations, anywhere between 0 and 14. Then I can say if digits are smaller than 10, between 10 and 14, sorry. If they are smaller than 10, I give a transport of 0. But I can do it also a transport of 14 and still be okay. The same holds true for the other constant. Now, I chose 12 and 24. You can choose whatever you want. My choice relates to the fact that I have to compare, actually I have to analyze a 5-bit number, which is the result of that addition. You know, in my first stage of the adder, this is what I have. 4 bits here, 4 bits here, and I generate now a 5-bit result. I have to inspect this one and to see if I'm here, here, or here. Then I have to determine the position of that by doing some kind of Boolean calculations on those 5 bits. My choice is probably the best for this case because it results in the simplest equations for determining where I am. Then D and C are actually telling me the value of the transport. If I am here, it's 0, 0. If I am here, it's 1, 0. If I am here, it's 1, 1. The way I'm computing them depends on where I place the constant. And these 12 and 24 are the nicest numbers that I can choose. You can try with different numbers. As long as they are in the range where the C value is legitimate, you are fine. Your adder will function. If you choose another constant which is out of that, you'll have a problem. You will have some kind of trouble because you will not get carry-free addition. Now, the second part of this question is how to deal with this result in order to make the adjustment depending on the transport, and also to absorb the transport coming from the previous position in the same time. And now there are two things in here. You have to use whatever you determine D and C in the previous stage in order to do the compensation. And what does it mean, the compensation? If you made a transport of 0, you have to do nothing. If you made a transport of 1, you have to subtract 10. If you make a transport of 2, you have to subtract 20. Now, because you are doing in two's complement calculations, minus 10 and minus 20 are equivalent with adding 6 and 12. Then I am using these two bits in order to determine whatever I'm adding to my value. That I take the previous values. There are the 4 bits because the carry out I just used for determining the transfer. Then I take those 4 bits and I add 0, 6, or 12, which I form based on the values of those. And what I do is I can also absorb in the same time a transport coming from my previous stage. You see in here, I had, this is stage I minus 1, and this is stage I. We both computed our positional sum, we both computed CI and DI, and in the next level, we do this kind of compensation. And I am compensating by adding 6 or 10, but I can also absorb a transport which is coming in the same time. And the transport is coming in a nice way because of the way I have chosen the representation of the transport. If both of them are 0, transport is 0, then there will be no contribution here. If the transport is 1, one of them will be 1 and the other 0. Let me see, because I don't know from the top of my head. Then if the transport is 1, C will be 1. Then it will contribute with 1 to this. And if transport is 2, both of them will be 1, and then the contribution will be 2. Then in this way, what I did is I am doing the correction and the absorption of the transport from the previous position in the same time. This is essentially the standard approach towards carry-free addition. I'm determining the dynamic range of the transport bits. They might be funnier than in this case. Sometimes I may have negative transport. Then I am determining the values of the constants. And I should make my life easier. Then I look at the constants and I see which constant is giving me the simplest equations for the transport bits. I also have to think on how I encode the transport bits whenever the transport can be larger than 1 or negative. And then I just have to do the conversion. Then I am compensating the position sum by adding, subtracting something, and I am absorbing the transport. And I'm done. You have faces which are a bit blank. I wonder why. Is it clear? Partially. Okay. Then you are happy in the beginning and you are getting more and more unhappy towards the end of the hour. Is that a normal phenomenon? Do you have questions on that? No. You have the right to get a break. Oh my God. But there is a contradiction between the one. I don't see that, right? Can you give me the benefit of the doubt that I can only see that? There is one more question which I'll briefly discuss after break, and then we return to our beautiful addition. Okay?